One thing that I say in common that some of actually you have not done, or you can actually improve further, would be first to highlight the changes on the ring transformation. That's the main thing, because when from phenol right to the end product, there are a few changes there. The core structure remains the same. Okay, the aromatic ring remains the same. All right, but what changed would be the side chain, and that helps in terms of the development of aspirin. That gives the responses what we're looking for in analgesic and also antipyretic. In 1940s, they only have corticosteroid, which is steroidal, and they have a lot of side effects. Yeah, those are being used before as anti-inflammatory, the only one. Yeah, you have, whenever you actually look at a drug, you have to see what actually happened, what people have earlier. Yeah, so if this is a reference, yeah, they need something which is easier to synthesize, safe, okay, and also you need something that is already taken, already active, okay. So what can they do next? So they use aspirin as a lead molecule. So they have this hypothesis, okay, that is based on, the first hypothesis is based on the carboxylic acid. They have tried to change, with aspirin, they have actually made derivatives based on the tetrazole. They thought that maybe the pH, the pKa is actually a big factor. Yeah. So they try to use tetrazoles, they try to use phenol to change it, and sulfonamide and so on and so forth. But they still couldn't get the same effect. They couldn't get the anti-inflammatory effect, the analgesic effect as well. That's what happened. So they have to go back to the carboxylic acid as the first hypothesis. You see later as well. Yeah? And the second hypothesis is that, so now they have one functional group already, the carboxylic acid. What is the R group? Yeah? So they look at the arachidonic acid, the substrate for this inflammation to causes the PG prostaglandin precursor. Yeah. So what is the R group? So when they actually look at the R group, they found that it's actually a long chain. Yeah. With alkene, there's 1, 2, 3, 4 alkenes there. Yeah. And they found that if you actually cut it short, 2 carbon or 3 carbon, what happens that you have this carboxylic acid there already, but you cut it short to 2 carbon, 3 carbon, like an acetic acid, nothing happens. It's really not much of, basically lacks any analgesic property. Yeah? If you extend it, if you have something like an aromatic ring or a heterocycle, yeah, alkyl chain doesn't work as well. You have to change it to aromatic ring or heterocycle because they want this interaction. Yeah, the alkene that is very important for interaction. So what mimics the alkene interaction, the pi-pi bond, is an aromatic ring. Okay, so and it seems that it correlates with alkene position at the 5 and 8 position. If they can make it bigger, it doesn't work as well. If the ring is bigger, it doesn't work. Yeah. So usually, if you see the rest of other NSAIDs, they are usually a single aromatic ring, right? Like the aryl acetic acid, aryl piperine acid, and so on. Yeah, usually like that. Okay. And another thing that they have found, the scientists have found, is that they are also non-planar. Usually, the ring, if they have another ring there, it would be nice to have a non-planar ring. This is exemplified by mefenamic acid, by Ponstan. I'll show you in a bit as well. Okay, it might be because it actually corresponds to this 8-11 alkene. So they need that carboxylic acid as a first hypothesis. They need for interaction, strong interaction, good interaction, to give the analgesic property. They need that pi-pi bond interaction. Okay, so that what gives a pi-pi bond interaction is the aromatic ring. All right.